Totally appropriate. Okay, so we have one. So here's the sort of plan for how we're going to finish up conformal maps here. So here's what we have left to talk about. So I want to talk about sort of one more structural idea, and then we're going to talk about interesting link-ups. So the last thing to talk about with conformal maps is called inversion on a circle or inversion across a circle, and we'll do that today. Once we have that, we're going to talk about, I can't talk about every possible application, but we're going to talk about a couple of applications to problems that arise in, like one problem from fluid flow, maybe a problem from electrostatics. So applications to physical problems, which is pretty cool. I'll get to remind you guys all about calculus 4, or vector analysis if you took it from me. And then I want to talk about some link-ups with some other areas of math. This is my third sort of set of ideas I want to talk about. I want to talk about how this connects up with linear algebra. And in the link-up with linear algebra, there's a relationship here between linear fractional transforms and matrices. So linear fractional transforms, and I'm going to use fancy terminology here, GL2C. There you go. 2x2 invertible matrices with complex entries. And then there's a way of understanding what's going on with this collection of objects algebraically. So not just linear algebraically, but algebraically. And then there's a whole bunch of research areas that branch off of this observation. Yeah, and then if there's anything left over that I haven't done that people want to see that they've heard about, then like any sort of bonus content will go there, which really just means, is there something within the scope of what I can talk about here? Like, I'm not going to solve your senior project for you. But you know, anything like sort of bonus content, if I can solve your senior project with complex analysis, I'd be impressed. And then from there, then we'll change topics to the second unit of the course, which should be about analytic continuation, zeta function, the gamma function, why the sum of the integers is -1/12, and also using contour integrals to do infinite sums. That'll be the second section of the course. So, okay, questions about anything? What week is it? 4? So I guess I have to give you guys an exam at some point. So probably what I'm going to do at the exam is, once we're finished with the conformal maps, I'll just give you guys, so we'll do one more homework assignment on this to cover the last set of ideas. And then after you guys have 3 homework assignments under your belt, I'll give you a take-home test to do. And we can discuss what the particulars will be. My impression, my impulse is to give you like I said, is to give you a take-home exam as opposed to having you do this in class. You can imagine how difficult it is to ask interesting or reasonable questions about this material to do in an in-class setting. Even given some of the stuff like the homework questions, even the easy ones, I think take some time. So anyway. Yeah, we'll talk about it. Don't worry too much about it, because this is not supposed to be a destroyer, right? And if I do destroy you on the exam, it won't be your fault that I do it. I'll try to avoid destroying you. And the way I evaluate such an exam would take into account the fact that I've destroyed everybody. That doesn't mean that you guys are allowed to play a game theoretic strategy where you all get together and deliberately tank the exam so that you can all do like every rat goes down with the ship sort of strategy. Although that would be clever. Okay, so what we're going to talk about today is called reflection on a circle. Okay, so the idea for this originally comes from the observation that we've already made, that if you start with the unit disk, so if you start with the unit disk T, so T here is the set of all z's where the modulus of z is equal to 1, and you pick a point z0 inside of it, and you draw a ray from the origin through z0. Then living out here is the point 1 over, let's call this just z, 1 over z bar. And if we put this in polar coordinates, if this is r e to the I theta, this is r e, so 1 over r e to the I theta. And so for a unit circle, again, the sort of original observation here is that this point and this point are in some sense reflections of each other. They stay on the same ray. You have this relationship too where you might notice, well, if I take this, the radius of this number, the modulus of this number, and I multiply it by the modulus of this number, I get 1. I'm going to point out that it's not the number 1 that's the magic here, it's the fact that's the radius of the circle that you're looking at is the deal. So the question that we're going to address is, well, can I do this idea? Can I take this idea and move the circle? And I put this somewhere else in the plane, because this would be a useful thing if I could take this idea of reflecting the inside to the outside. You can imagine if you did this with all the points inside of the disk, if you took this to be a map, z goes to 1 over z bar, and you use this as a map where what you plugged in was the unit disk, then what would come out, I guess maybe we can, I don't know what its symbol is here for, I'll call it d hat for right now, which you can think of as the outer disk. So what goes in is this set, and what comes out is this one. But it's a special sort of inner-outer reflection. Yeah?
So we've seen maps that take the circle to the half plane, and if you apply those again, you get to the outer disk. Is that the same thing?
So not quite, because that doesn't get you, so getting to the outer half plane, getting an inner circle to an outer circle, we did one in the homework, right? The 1 plus z over 1 plus 3z is one that does inner circle to outer circle. It doesn't keep the circle invariant is the first thing. But the second thing is, this one explicitly preserves the angles of all of we're going to call this one the reflection across the circle because it doesn't just do inner to outer, it actually preserves the angles.
Is there a way to write it as a different thing other than using conjugate?
No, so that's a theorem that we're going to prove is that any one of these reflection across the circles is going to be a combination of conjugations and a linear fractional transform. So the conjugation is a necessary component here because if we're trying to take a point and land on the same ray, the only way to do that is we have to destroy that like positive theta to minus theta angle thing because we want to bring the negative theta back to positive theta. So there must be conjugation involved. A better way to think about it is that what we're going to end up doing is intrinsically, we're going to start with a circle, we're going to map it to this circle, we're going to perform the reflection, and then we're going to compose that with taking it back to the original. That doesn't show up in the specific way this is done in Marsden, but that's what's really happening here. It's a composition of maps like that. Okay. I guess the other way to view this is if you have a Riemann sphere and you have a unit circle on it and you start underneath, then this maps. What am I doing? It's not a Riemann sphere. It leaves the circle invariant, but you get the upper cap instead. Right, so it's like a reflection from the top to the bottom. That's the way to think about it. Okay, so what we're going to do now is we're going to try to take this idea and look at it just geometrically to see what the implications would be if we had a circle that was centered somewhere else. So can we leverage all this like sort of nice math that happens on the disk and the unit circle and with these points in the case where I have a circle that is not the unit circle? So we're going to let C be a general circle. Ultimately, we're going to include lines, but for now, we're just going to start with the circle case and see what the circle case says. So let G be a center circle. I don't know why not. Let's just throw it in now. Does that mean I have to use the word clerical again? No. Let C be a general circle. I'll just use the parenthetical or line. And if you want to put in your notes, you could write clerical. You sick bastards. The clerical? No, just do this. Just do this. Forget the clerical. All right, throw it in. Use the clerical. And let's let centered at Z naught. That doesn't really make sense when we're talking about a line, which is why we sort of shave off the line case. Then, all circles that pass through a point Z that is not in Z and intersect C at right angles intersect each other at a unique point Z tilde. Because why not? More symbols. Z tilde. So I'm going to draw a picture of what this statement is. Okay, so I don't even know why I erased the unit circle, because I had used it. So this is easy to understand in the line case. So if we think about the line, if I put a point Z naught in the plane, sorry, this is the line, I put a point Z in the plane, this is my set C, circle. If you start drawing the family of all of the circles that pass through Z and that also intersect this line at right angles, so let's see, here's one. That's a circle through the point of infinity. It passes through at right angles. And then there's another one that looks like this. Passes through at a right angle. Another one that looks like this. And eventually you're going to get to the biggest possible arc. There's this sort of unique circle of maximum, that has this as the center. And this is the radius that kind of looks like this, right? There's a whole family of these circles that pass through Z. What's that?
Isn't there a circle that...
Not that passes through at a right angle. If you go any further than this, you're not going to have a right angle anymore, right?
Right.
Like if you put a circle...
Riemann sphere, you could, if you had like effectively the great circle. Or that
But that's this one.
Oh no, I guess it wouldn't be a great circle because it wouldn't go through 0.
Yeah.
Like the great circle through that point. So
Yeah, I mean this line represents the great circle that passes through Z and this sort of unique perpendicular point on this circle. So that sort of represents that great circle thing. So yeah, you got a circle of radius infinity that passes through Z, and then the other sort of largest circle in this family has this radius. Smallest. Yeah, because as you take the center and you slide it away, right? Essentially what you should think here is these circles have centers that are out here somewhere, right? Like as you slide that point away, you're going to get larger and larger radius, which means you're going to get a tighter and tighter circle, like arc between here and here. Okay, now it should be believable to you from high school geometry, without any proof at all, that there's going to be a point down here where the reflections of all these things. If you imagine that circle that passes through Z has a center that's on this line. It's going to come down here and it's going to pass through this point, and that arc will be repeated on the other side right here, right? And because the reflection of this is going to be the same image, there should be a unique point down here. So we call that point Z tilde. Z tilde is the reflection of this picture on the other side of the half plane. I mean, that point should exist because, again, there's going to be that reflection is easy to draw because you just draw the line segment of the same length. And then if you imagine the center of the circle was right here and Z was on a diameter, then when you swept the diameter around, those two circles would cross at the same point. And every other circle that you draw through Z that is right to this line also should pass through this point Z tilde. Okay, so that's sort of a slightly hand-wavy, but I think pretty straightforward geometry to see that that must happen. So now what are we going to do if C isn't a line? What if instead, okay, so this is the line case. This happens when C is a line. What if instead we have the case where instead of C being a line, C is a circle centered at Z naught, and I have a point Z that I choose. Maybe I'll choose it down here so I can be neater. There's a point Z, and I make the same argument. It should be the case that if I draw all of the circles passing through Z and that pass through C at right angles, that we should get a unique reflection on the outside. Why should that be true?
Doesn't C have to be outside C?
Is that?
Doesn't Z have to
It could be inside or outside.
Z not.
Not
on
in,
C,
not
okay.
on C, yeah. So if Z is on the circle, then we're going to end up defining the reflection of Z on the circle just to be the point itself. It's like reflecting across the x-axis. If you're on the x-axis, you are your own reflection. Yeah, so not, when I say not in C, I don't mean inside in the Jordan curve sense. I mean not actually on the circle. Okay. Well, I'm going to remind you guys that we're in the section of the book called, or of the class called conformal maps. And conformal maps have this wonderful property where they preserve angles when you apply them to things. And I'll remind you that disks can be mapped to half planes, right? So what we're going to do is we're going to say, find a conformal map that takes this circle on the boundary to the real line. So we're going to find a T that does the following. It's going to take T of C is going to be the real line. Okay. So that means the circle that was at the edge, which maybe I'll draw this color. So we take C and we put it on the real line. And we take Z and we map it through T. So T of Z we will call W. So maybe there's W right there. And I'll make the observation that if you drew some other curve that passed through Z and also passed through this at a right angle, so these are all lines that go through, that's not really the right angle, but imagine that it was. If you drew sections of circles that pass through Z and also cross the circle C, perpendicular to the tangents to C, well, the images of those circles are going to look like this. And the reason that they're going to continue to pass through at right angles is because conformal maps preserve angles. Yep.
But aren't conformal maps not guaranteed to be conformal on the boundary?
So in this case, I guess the way that you think about this is when we're doing, so it is the case that when we're talking about simply connected bounded regions with simple, like continuous boundaries, we had a theorem that said that it was enough just to track what happened to the boundary. So in this case, it's the fact that the map extends by continuity to include the boundary. So if this is a simple, if this is a bounded, not even bounded, it's just a simply connected set with a continuous curve that dictates the boundary, the map will extend to the boundary by continuity. So it's not conformal at the boundary, but it extends continuously there, and that means in any neighborhood of that point, the function exists and you're still going to get that right angle preservation. Okay, so the fact that you can do this follows from the fact that every simply connected set is conformally equivalent to every other simply connected set. And if the boundary is nice, then you can always map boundaries to any other nice boundary of the same type. So these nice boundaries are called Jordan curves. Probably Jordan. Okay, well then you just say, well, now we're back in the line case again. And the line case implies that there must have been this point down here called W hat. So the line case that we already wrote implies that this is true. The conformal maps between simply connected sets are invertible. And so that means that W hat must have come from some Z hat. That this must have been equal to T of Z hat for some Z hat. And because the images of all the curves cross are, like that point is on the images of all these curves, it must also be on the curves that it came from originally. So you get like this sort of, all of these things meet up at a point Z tilde.
The red lines would keep going on forever.
What do you mean?
Like you could have.
Yeah. I mean, so like, I actually finished up I just didn't want to draw all the circles because I wanted to assert that this point existed before I finished up the lines and finished them. But yeah, if you just started drawing circles, the beautiful thing about this is you can always find this point just by drawing 2 circles. If you're trying to work numerically, you draw 2 circles that pass through this point and hit the circle perpendicularly, and wherever they cross is going to be the reflection. Okay, so the big picture of this theorem is exactly that proof, right? And a lot of people don't even remember how the argument works, this sort of reduction to the linear case. You just remember the picture. Oh, I have a circle, and it looks like this. I'm going to be the axis here. I have a circle. It has some center Z naught. I have some point Z. And out here somewhere, I have, so there's a circle connecting these guys, and then there'll be a circle that looks like this, and it kind of goes. Sort of, this is the picture that people carry around. I didn't do a good job of that. No, this should be right. Right? Looking at my own notes. Yeah, it's okay. Yeah.
Maybe I'm really investing on geometry, but circles have many equal distances, right?
Well, the center of these circles isn't.
They're all different than that. Exactly.
Yeah. So again, what you should imagine is there's some line, just like in the case when you're working in the line case. How there's this axis where the center of the circle runs away, and you end up with these arcs that start looking like a half circle, but as the center runs away, the arcs become shallower and shallower. There's this axis here where the centers of these circles could run this way, in which case it pulls the arcs closer to the line. And then if it ever reaches infinity, you're flat because now you've got an infinite radius, and so you're just a straight line.
But Z tilde is small.
Yeah, but that's the point, is this axis is sort of precisely between these guys, right? It sits between Z and its reflection to set up the axis on which the center of the circle runs.
So that makes sense. So like the actual circle for the shallowest.
Yeah, the actual circle for the shallowest one is this enormous, it's this huge circle, right? And then the bigger you make, and that would have center right here, and as you pull the center out, you're pulling the circle flatter.
Is there a formula to find for that?
Yes, the next thing we're going to do is write down what the formula is. So it's easy in the case of the unit circle. In the case of the unit circle, Z tilde is 1 over Z bar, right? That's the sort of... So this is an excellent question. How do you find Z tilde? Because if I want to use this map, I have to know what the map is. So if your circle C... What's that?
Why would you want to use this? What would it be used for?
So you use this because reflection is the simplest possible way to act, because you're staying preserved with respect to your original. I mean, so here's the big deal is, I want to keep everything on the same rays, but I really say I've got some sort of singular point on the inside for a function on the inside of a domain. But it's controlled as I run away to infinity. So you can imagine, suppose you have a function sitting over this picture that has an infinite spike on the inside of the disk, but decays away on the outside. Right? That's it's like a 1 over e to the z type thing, right? So if you flipped the domain if you did this sort of reflection inside to outside, you keep all of the angles the same, which is nice. And the radii are going to turn out to have this really nice relationship between this distance and this distance will turn out to have a really nice geometric relationship. And then you flipped the bounded behavior to the inside and the unbounded behavior to the outside, which is much nicer. So it's like you can think about trading a Laurent function for a Taylor series. As long as you're willing to flip the domain, you go from something that has a pole to something that has a 0. Yes? What's that?
It's not possible to be small.
No. Okay, so if C was equal to the unit circle T, I mean, we're going to see this formula when we look at some of the physical stuff that we're going to talk about. This shows up. If C is equal to T, then z tilde is just 1 over z bar. That's kind of like we should expect whatever formula we get should reproduce that. Okay. Here's what the formula looks like. Okay, z tilde is equal to z naught bar z plus r squared minus modulus of z naught squared over z minus z naught all bar, where z naught is the center, r is the radius. If C is a line, it's just the reflection across, like perpendicular reflection across the line. Does that actually do what we want it to do? Does that turn into 1 over? Yep.
Just wondering, like, because like in complex one, you said like if anything has like a bar in it, it's like probably not.
Ah.
So like.
So these are not analytic maps.
So if
It's almost analytic.
C is a line, in a colloquial sense, we'd say that the center is at infinity and the radius,
Yeah.
right? If you plug those numbers in, you get like nonsense.
So the way to do it there is like it's easy to find the reflection point because you just calculate
So
the.
there's if r is less than infinity, and then
You were just
if r is
reflect.
infinity,
If r is infinity, you just reflect across the line. Reflecting across the line is easy,
Right.
right? Yeah. So this is strictly the actual circle case. Yep.
Isn't analyticity prerequisite for conformality?
So this is almost conformal, and you don't need. The thing is, you can have maps that are conformal. If every analytic map with non-zero derivative is conformal, right? But conformal didn't have anything in. Conformal formally means that you're an angle preserver. All it means is you're angle preserving, right? If you feed in a function and you calculate its derivative, then what comes out the other side is a constant rotation of that, right? It's a nice thing that analytic functions are all conformal. This is going to be a set of things that preserve angles but flip the orientation of curves instead. So instead of a forward rotation, it's a backwards rotation. So it's like, these are called it's in the sense, conformal maps are either analytic or analytic maps, how do we even say this? There's anti-analyticity running around in the background too, because the other way that you could preserve angles would be you go in like this and you rotate. That's one way to do it, right? The angle orientation is the same here as it was here. And no matter which two curves you plug in, the rotation is always the same. That's what we mean by conformal. If instead what I do is I flip the orientation of the angles and rotate consistently, that's not an analytic map anymore, right? Because I flipped positive angles to negative angles to do that. But I still preserve the distance between the angles by doing it. So I'm still sort of conformal in that sense, that like angles are still angles, but I'm rotating the wrong direction. So these maps are useful, but they do flip. I mean, you should imagine there's flipping that happened here because we took the natural reflection of 1 over z, which has that theta to negative theta, and we undid the negative theta by barring it to bring it back in again. And as soon as a bar is involved, we're not analytic, we're anti-analytic, which is not a word you're allowed to know. So you got to forget I said it. You have like an anti-analytic version of the Cauchy-Riemann equations, for example. Right? You just put an extra negative in Cauchy-Riemann equations, and you've characterized the maps that are anti-analytic maps because they're orientation reversing instead of orientation preserving. And that actually allows you to work with power series in Z-bar.
It's for the mix.
What's that?
So Z-bar is not bad, it's just mixing Z's and Z-bars.
Mixing Z's and Z-bars can give you all kinds of problems because then you have like, a power series in Z-bar is anti-analytic, a power series in Z is analytic. You start throwing Z's and Z-bars together and you have like, some terms may preserve orientations and some terms may flip them, and like it's harder to keep track of what's happening. So like you see this in multivariable function theory where things that mix Z's and Z-bars are, you can still treat them. Like it means something to have a series in Z and Z-bar, it's just like more complicated to deal with. Okay, yeah, so let's point out here, the map z goes to z tilde is not analytic because it involves z bar, but it's almost analytic. So the map z takes, z goes to z tilde is a combination of linear fractional transforms and complex conjugation. And so what you should think is, okay, so what's happening here is linear fractional transforms, that is conformal and analytic. And z bars, that can flip orientations, but angles are still like, it's still invertible in the sense that like angles are preserved, they're just flipped. You can see that reflected in the formula here. I will point out that if z naught is equal to 0 and r is equal to 1, this formula reduces to that one. Okay, so what other features does this map have? So the nicest thing about reflections is this. If T is a linear fractional transformation, and C is a clerical then T of the reflection of Z is equal to the reflection of T of Z. That's because of the angle preserving properties of linear fractional transforms. So the word version of this is LFTs preserve reflection across the circle. Which is nice. It means that you can reflect and then continue to transform the domain, and it's recoverable when you're finished doing that. Okay, so here's the big proposition about these guys. All right, so here's your proposition. 1. The reflection of a point is the point. It's a useful feature for a reflection to have. 2. The map Z takes, Z goes to Z bar is conformal. Oh, sorry, not, I'm sorry. And according to our definition, it's not conformal, but angles are preserved in magnitude. And reversed in orientation. I will point out one of the complications of using the word conformal is that every author means something different. Some authors mean biholomorphic, which means there's no such thing other than like invertible conformal maps. They don't even consider maps that aren't invertible in terms of what they mean when they say conformal. Some use this one. That is not even legible as the word angles. We're working with Marsden's definition at the moment. Property 3, obviously if C is a line, and Z tilde is the sort of perpendicular reflection across the line. And then Z to Z tilde maps circles to circles. Clericals to clericals. And that's a nice feature as well. So basically, up to whatever your particular understanding of the word conformal is, these are essentially in all important facts, these things act like conformal maps, right? In the way that we taught them. They preserve angle but reverse orientation. They map circles to circles. They're invertible, right? So they're not. It's a nice sort of reflection. It's like just about as close to conformal as you want. Okay, so that means that probably what I should do is ask you guys a question about, like, what sort of question should I ask you about inversion across a circle? Now, there's at least one of you in here that is, like, intensely familiar with reflection across circles. So, what does inversion across a circle do in the Riemann sphere? That's a good place to start with this. Well, remember, this works in a general circle, right? So let's actually see if we can visualize. And again, I keep telling you guys, like, you know, we're going to get used to the Riemann sphere just by I'm going to continue getting you used to it, right? So you've got a circle. It's floating around in space somewhere. See? You have no idea if it's the unit circle, so you can't say bottom to top. So here, you want a coordinate system? There you go. There's a coordinate system. Yep.
So, I guess you could envision it as like two coupled rotations, right? Or could you envision it as like pushing the sphere through the circle, like a quaternion multiplication
Okay.
almost, and coming back on the other side?
So that actually, so the idea of pushing the bottom sphere through the inside of the circle is like an interesting way of, because that's actually going to get you the orientation reversal if you do it that way, right? So what you're imagining, I'm just trying to think about what you said here. This is where these math classes get weird, right? So you got a sphere running around, and on that sphere, you take this and you map it over to the sphere somewhere. So here it is, right? It sits on the Riemann sphere. Is it still a circle in the Riemann sphere? Yeah, right? I mean, the idea of taking the plane and putting it into the Riemann sphere, circles stay circles when you do this in the stereographic projection. Got that? Constantly writing Pac-Mans and Death Stars in here. Okay, so now what you want to do, if this thing was made of cloth, so here's what I want you to, this is what I imagine when you say that. This ring, this is a metal ring, and you're punching your fist through the metal ring and stretching what was in the circle to the outside and pulling the rest of it around the back to make the inside?
Not like it's cloth. Like in the same way, we can take the unit circle to a line through a rotation and take it back to the outside circle. Do that, except one dimension higher in the sphere. So take that sphere to a plane that goes to that circle, and then take it back so that you reverse orientation.
Okay, I think you're right, but I want to do this in a way that that maybe like I can try to make it clear what's happening more broadly, if that's okay. I think you're right, but instead of decomposing into a bunch of rotations, can you imagine like the set of rays that come out of the point? Right, the whole point with the Riemann, with the reflection across a circle, is that the rays stay. Everything that was on a ray stays on that ray, right? So the rays are invariant. And that's what the word invariant here means, that they stay the same, right? So after you apply inversion across a circle, the circle didn't move because that's sort of the locus of the reflection. And then you have this inversion that happened where the rays are still there. Since the circle didn't move and the rays didn't move, but you've got now the inside of the disk is now the outside. Is it easier to picture what's happening on the sphere now? The idea is, if you wrote the center of the circle here and you started tracing out rays, so what do rays look like on a sphere? Rays through a circle, if I put them in the Riemann sphere, what do they look like? It's like, you think about this as like the North Pole, right? You have a bunch of great circles that point out of it, and they have to be through some sort of antipode out here, right? And then they come back around, and then they go like this. They're going to have to pass through the point at infinity is the idea, because these are all lines, right? Lines on the sphere pass through the point at infinity. And every single ray that you draw corresponds to a great circle because it passes through this sort of are they great circles, actually?
I think they're I think they are great circles, but do they all go through infinity?
They're not great circles
I don't
because
think
they go through infinity. Well, they have to go through infinity. They must. They're lines, right? Every one of these passes through infinity, but it doesn't pass through the antipode to infinity. So actually, I'm wrong. They can't be great circles. They're circles on the sphere, but a great circle through infinity. Do you agree with me that infinity is at the end of every one of these? Right? These are lines, and so I know the absurdity of writing infinity at the end of all of them, right? They all pass through infinity. Do they pass through the antipode to infinity? No, they don't, right? There is one line that passes through infinity and 0 that goes through this thing. So this particular ray will be the great circle that runs between infinity and 0. But all the rest of these points must run through infinity. And if they have to run through infinity, yeah.
But if they go through infinity and they go through the point at the center of the circle, two circles can intersect at a maximum of 2 points on the sphere, so they can't also go through the antipode.
That's right. So they can't be great circles that run through infinity and 0.
Yeah.
Yeah, that's the idea. They're not. That's, in fact, when I started drawing the picture, it's obvious that they're not great circles, right? Because if you tip this ray over and you draw the circle.
So does that mean they all?
Yeah, so we have to be more careful about the way we drew this is the idea. So let's try again. I was drawing this not in sort of Euclidean geometry, but it's not because remember, everything out here is being pinched up to the point of infinity, right? So let's try this again. This is the problem when you try to run infinite, like weird Riemann geometry on the fly. Okay, so there's the center of the circle, and we know every one of these rays must go through the point at infinity. It has to, right? Now, anything that crosses through the circle at a right angle here is still going to cross through this sort of bent circle at a right angle here. And so you're going to end up with these circles that come through like this, but then they have to twist back to get through the point of infinity. And I guess they're going to do something like this and come back around here. And if you go this way, then you're going to pass out, you're going to cross through the point of infinity, and you're going to come back around like this. Now, it makes sense that they all stay in the upper hemisphere because these lines above a certain slope, yeah, my geometry needs work. Does this make sense, what I'm doing here? Comes out, it has to go through the point at infinity, so it comes back through like this. It goes out, it has to cross through the point at infinity, so it's going to come back through like this. So you get this family of circles that sort of give you this coordinate system on the sphere. And the idea is that every point here on the inside got mapped somewhere out here on the outside. There's sort of, you still have this reflection relationship between the inside of the circle and the outside of the circle after you do the reflection. But the point is, this doesn't change those lines. The map that takes the inside to the outside did not change where the lines were. So it gives you a consistent way of locating things on the sphere. Yep.
So the only way to send rays to great circles is if you invert without a circle instead of a double.
You have to have the origin involved, yeah.
Right.
Which is fancy.
This is like the weird Riemann translation, maybe like graph hole.
Yeah, it's related to the idea of like sort of you're distorting things. I mean, you're going to do this because you imagine as when you translate with a linear fractional transform, in the sphere what you're doing is you're taking a nice longitude-latitude system and you're taking a single point and then just that point kind of squeezing the whole system over, which torques the longitude-latitude lines. So this is going to, if you drew all the circles that sort of were concentric with this and came out, you would end up with something that looked like, you know, oh, I'm going to draw myself a little local coordinate, like polar coordinate system. You're going to end up with these concentric circles on the sphere, and so you still end up with something like a latitude-longitude system, but it's a distorted latitude-longitude system.
Do they end up still concentric on the sphere?
Yes.
Like they have to stay circles.
I mean, they're still circles, and they still have the, okay. We've got to be careful about what we mean by, like, they're not going to be concentric in the sense that their Euclidean distance from here to here is going to be the same all the way around.
Right,
it's still a circle. This is still the center in the sense of Euclidean center, but a Euclidean center to like this sort of spherical radius. Remember, a radius pointing out in one direction and a radius pointing out the other direction here corresponds to a big radius pointing down towards where numbers are small and a small radius pointing up to where numbers are big. right? On the Riemann sphere, the closer you are to infinity, the more crushed you get. So they're circles, but they're not, they sort of pile up like this. You have a set of concentric circles around a center, Z naught, and what you end up with is a set that looks like this. If you do the Z tilde map, you're going to end up with a set of circles where you have this point right here, and the circles around it are kind of crushed up like this.
Right, because they have to approach infinity on one side, and they also have to approach infinity on the other side, they have to get there at the same time.
Yeah.
Right?
Yep. Yep.
How come they don't become ovals if you have like?
Because of the weirdness of the stereographic projection, right? So the stereographic projection itself guarantees that you can just calculate directly that if you put in the same thing we did where we took the quadratic equation for a circle and plugged it in and what came out was an equation for a circle, the same thing happens. The reason that they can stay circles is because they slide, where that is not guaranteed to be the geometric center of the circle anymore in a Euclidean sense. Yeah, the weirdest thing about the Riemann sphere map to me is that circles are circles. It's beautiful but weird, right? So. Yep.
What did you mean by they say spherical when you have a great circle?
I mean, I was going to say something wrong, and so I stopped myself. I said the first half of a sentence, realized the second half was going to be wrong, so I just stopped and hoped nobody noticed. But you did. All right, so that is